All right, guys, I hope that you are staying healthy and productive while at home. All right, in this part of the lecture, we're going to be switching from the treatment of homogeneous equilibria, in which all of the reactants and products were in the same phase, to now talking about heterogeneous equilibria processes, in which one of the substances, one or multiple of the substances that participate in the reaction are in the solid phase. And we're going to be introducing a new type of K that is associated with this dissolution process. So let's go ahead and get started. This is section 17.6 of your book. All right, so again, what we're going to be talking about mainly is going to be equilibrium processes in which we have a heterogeneous reaction occurring. Heterogeneous is talking about basically the fact that we're going to have substances that are in different phases. Specifically, some of the substances are going to be solids. And so let's talk about when this would happen. So there's two specific types of reactions in which this could be what's happening. One of them is a precipitation reaction, which is something that you should have learned in General Chemistry 1. This was a type of metathesis reaction or a double exchange reaction in which two reactants, two ionic compounds, would actually exchange their ions in order to form two new products. And one of the products was a solid, so you would have precipitation or formation of that precipitate in the reaction. The other process is that we could have a solid compound, what's typically thought of as an insoluble compound that is placed into water. And even though we consider the compound to be insoluble, in reality, those insoluble compounds actually do dissolve to a certain extent, even if it is a very, very small extent. So the equilibrium processes that we're looking at here in this dissolution is the equilibrium between the solid reactant or the solid compound that you have added and the dissolution products of that or the products of that dissolution, meaning the ions that that compound is made out of. So let's look at this example here. For example, this is an example of this dissolution process in the way that it is written. So we have a solid compound XY. It is an ionic compound that has a cation X and an anion Y. That compound is labeled as S for solid, meaning that according to the solubility rules, we consider this compound to be insoluble. But as I mentioned, in reality, even those insoluble compounds do dissolve to a certain extent, and that dissolution process is what we have written here. That means that that compound is going to separate, even if it's just to a little bit of an extent, into the X cation and the Y anion. And that is an equilibrium process because all three components are present at the same time in the solution. And it is a reversible process as well. And so for any equilibrium process, remember that we can write an equilibrium constant expression, which we have talked already about, just K, Kc, Kp, Ka, Kb, Kw. So you guys are very familiar with them. Remember that we always write them by putting the products divided by the reactants, with each of them raised to the coefficients. In this particular case, you can see that we have put the concentration of X, which is our product, or X plus, the concentration of Y minus, which is our second product, each of them raised to the power of 1 because our coefficients are 1. But then we have not included XY in the denominator. And the reason for that is that, if you remember, we actually do not include solid compounds in the equilibrium. And the reason for that is that we're assuming that they are present in excess, and so their concentration is basically treated as if it was constant. You can think about it like you have a huge amount of this solid relative to the products, and so the concentration is maintained more or less constant. And that's the reason why we don't include those solids. Now, that Ksp is the equilibrium constant associated with the solubility product, but again, it's basically the same type of idea that we have used for Ks in the past. We now call it Ksp to indicate solubility product. All right, So as I mentioned, solubility or reactions that are heterogeneous include two different types, both precipitation reactions as well as dissolution processes. And they're both going to be represented by this KSP expression. So in this particular example, what I'm showing on the right-hand side is the reaction between a lead compound, something like lead nitrate, let's say, and another compound which it's a source of iodide ions, let's say sodium iodide or something like that. When these two compounds are reacted together, what happens is that these two ions are going to come together to form lead iodide, which according to our solubility rules is insoluble. And so this is our precipitate. And you can actually see that precipitate forming here. That yellow compound at the bottom is the precipitate, and it is insoluble, it's a solid. Now, in order for us to look at the equilibrium process that has happened there, the convention is that we actually write it in such a way that we take the solid and we dissociate it into the ions that it's made out of. So we're kind of looking at the reverse process where the solid now is dissolving into the ions. And notice that the products here are AQ, indicating that the ions are in solution. And then we can write a KSP expression or solubility product constant expression for that process by taking our products concentrations, multiplying them by one another, and notice that here we have the concentration of the iodide raised to the power of 2 because the coefficient for that particular ion is a 2. That coefficient, that is something that you guys will need to be able to figure out on your own, and you do that by basically balancing the equation. You look at your compound, you dissociate it into the two ions, and then you look at how many of those ions do I need in order to balance the equation. Since in the lead iodide you had 2 iodide ions, you needed to have a coefficient of 2, and of course that 2 ends up here as an exponent. All right. Another example here is for this compound barium phosphate. It is a solid compound. We can write the dissociation of that solid compound into the ions. The cation is the barium ion, and we know that barium has a charge of 2+ because it is on group 2 of the periodic table. So we write it right here. We then know that the anion is phosphate, which is PO4 with a 3- charge. And notice that you can also, in most of the compounds, you can also figure out the charges by looking at the formula of the compound. These 3 here belongs to the charge of phosphate. This 2 here belongs to the charge of barium, and that's what ends up being here. And then after that, we balance the equation by putting coefficients on the ions. So for the barium, we needed 3 barium ions, therefore we put a coefficient of 3 here. And for phosphate, we have a total of 2 of those ions in barium phosphate, so we're going to put a coefficient of 2 here. From there, we can now write our equilibrium constant expression, or KSP, by taking the product concentrations, each of them raised to the coefficient of each of them, so 3 here and 2 here for the phosphate. And of course, we omit the barium phosphate because that is a solid compound which does not participate in the equilibrium. And just to remind you, both solids and pure liquids do not appear in the equilibrium expressions, and each of the concentrations are raised to the powers that are equal to the coefficients. All right, let's go ahead and do a couple of examples. So the question here is, write the KSP expressions for the following compounds. We have 3 solid compounds. These are 3 independent problems. We're going to start with the first one, the calcium fluoride. So we're going to write a double-sided arrow to indicate that we have an equilibrium process. We are then going to separate that compound into the 2 ions. The first ion is the calcium ion. And we know that calcium is from group 2 of the periodic table, so its charge is going to be a 2+. But notice that I can also figure that out by looking at the formula. This 2 belongs to the charge of the calcium. And then I can put my second ion, which is fluoride ion, and I know that fluoride has a charge of -1 because it is in group 7 of the periodic table. I then need to balance the equation. According to my formula here, I had 2 of those fluoride ions, so I need a coefficient of 2 right here. From there, we can now write our equilibrium constant expression. I'm going to write it as KSP is going to be equal to the concentration of our products, which are going to be the calcium ions times the fluoride ions. The calcium had a coefficient of 1, so we don't have to raise it to a power, it's just to the power of 1. But the fluoride is going to be to the power of 2. Now we're going to do the second example. In the second example, we have silver sulfate. Again, we do a double-sided arrow. We're going to then separate it into the two ions. In this case, we're going to have silver ions, and I'll come back to the charge of that. And then we're going to have sulfate ions, SO4. This 2 is the charge of the sulfate, and that's a 2 negative, and that's something that actually you should have memorized in General Chemistry 1. And silver, notice that there's nothing around the sulfate. There's no number outside of the sulfate. So the charge of it is positive 1. And actually, the charge of silver is positive 1. You guys might remember that diagonal that I showed you on the periodic table. With silver is positive 1, zinc is positive 2, aluminum is positive 3. They are in a diagonal next to each other. So again, silver is positive 1, zinc is positive 2, aluminum is positive 3. That should be something that you should remember. The last thing that we have to do is to balance the equation. And so if we look at the formula, we can see that we had 2 of those silvers. So therefore, we need to put a coefficient of 2. Now we can go and write our KSP expression, which is going to be equal to the concentration of the products, which the first product is silver ions. In this case, this is going to be raised to a coefficient of 2. And then finally, we have the sulfate ion to a power of just 1 because its coefficient is a 1. Last but not least, we have calcium phosphate here, which is very similar to the previous problem. And basically what we're going to do is, again, separate it into the two ions, calcium ions. We know that calcium is in group number 2, so we're going to have a charge of 2. Notice again that this 2 is the charge of the calcium. And then we're going to have the second ion, which is phosphate. Phosphate is going to have a charge of 3 minus. You should have known that by memory already, but also you can see that that 3 was the charge of the phosphate. And then finally, we're going to balance the equation. I need 3 of those calciums, so I'm going to put a coefficient of 3. And I need 2 of those phosphates, so I'm going to put a coefficient of 2 here. And finally, our KSP expression is going to be the calcium ions to the power of 3 times the phosphate ions to the power of 2. Again, we omit the solid reactant. A couple of things that I want to mention. Again, you have to be able to break up that solid into the ions and be able to balance the equation. You want to make sure that you're actually putting the ion in its ionic form, meaning including the charge in your brackets. And of course, don't forget the coefficients. Another thing that I want to warn you is that you need to know what the ions are. For example, I get a lot of people that might actually say that here my ion is F2, but F2 is not an ion. The ion is fluoride, and you needed to know that by looking at the periodic table. Like you know that elements in group 1 form an ion of positive 1 charge, like sodium Na+. Elements of group 2, like calcium, form ions that are 2+. Then if we go to the right side of the periodic table, elements in group 7 form a -1 anion. Elements in group 6, like oxygen, form a 2- charge, etc. So those are things that you need to know. And of course, you also had a number of oxygen ions, like sulfate and phosphate, that you were expected to know from a long time ago. All right. So later on, we're going to be utilizing these equilibrium expressions to be able to figure out either the solubility of the compound that is solid, or figure out one of the concentrations of the ions that are in the solution. And right now we're going to be looking at the differences in the definition of solubility versus the solubility product constant. You need to make sure to differentiate those two terms, even though they share a word, right? So whenever we talk about solubility, We are talking about the amount of solute that dissolves to form a saturated solution, meaning that we're basically saying that this is the maximum amount of solute that can dissolve at that particular concentrate, at that particular temperature. And so it is a measure of concentration. And because of that, its units are going to be concentration units, such as grams per liter or mole per liter, which is molarity, or milligram per milliliter, or something like that, something that represents quantity of material divided by a specific volume. Now, this solubility changes with conditions. As we know, for ionic solid, the solubility will increase with temperature. For other compounds, like compounds that are gaseous, it will change both with temperature and pressure. So this is the solubility. Again, it's the amount of material that will dissolve in a particular solvent at a specific temperature. On the other hand, the solubility product or solubility product constant is the equilibrium constant, or the K, for the equilibrium between an ionic solid and its saturated solution, meaning and the ions that are dissolved into the solution. It is abbreviated as KSP. It is unitless, just like all of the other Ks that we have worked with, and it is constant except for temperature. It does change with temperature. Another thing that is important is that the solubility product constant is related to the solubility, in that it is a measure of the compound solubility, but they are not the same. And so I want to make sure that you guys know. In an exam, I will ask you either for the solubility, which means I'm asking for a concentration, or I will ask you for a solubility product, which means that I'm asking you to find the value of the KSP. All right, so I mentioned that the KSP is a measure of the compound solubility, and that's what I want to talk about in this particular slide. So here again, we have a fictitious ionic compound that is a solid, meaning that it's an insoluble compound, and that one is in equilibrium with the dissolution products, which are the ions that it is made out of at some concentration. We write the KSP expression for it by taking the concentrations of the products, each of them raised to their coefficients, and omitting the reactant because it is a solid. Okay, so this is something that we have already talked about. Now, how is this a measure of solubility for that compound? Well, if you look at this, it says that the larger the KSP, it means that the larger the concentration of the ions in the product are, right? And so that means that more of the solid compound has actually gone on to make more of those products. And that means, that the solubility is larger, right? So if the KSP is larger, that means that the concentration of the products are larger. That means that the reaction has gone forward, dissolving some more of that reactant. So in a way, we can say that the opposite would be true as well. If the KSP is really, really small, that means that we have very small concentration of the ions. That means that the reaction has not gone forward very much. That means that the solubility of the XY compound is very, very low, right? So lower KSP values are generally indicative of lower solubility, meaning that the reaction is going to favor the solid reactant as opposed to favoring the products. But this is not always the case, in that you cannot directly compare two compounds for their solubility just by looking at the KSP. In certain cases, you can do so in some cases, but not in other cases, and that's what's talking about here. So this is in general, but not 100% valid all the time. Okay, so what I do want you to look is at this. So one can only compare the relative solubility of two compounds by their KSP values if the compounds produce the same number of ions in solution. And all right, so just to make sure that you guys are following, remember that before when we were talking about weak acids, we said that a weak acid that had a larger Ka was the stronger, meaning that it would dissociate more into ions. Here we're saying that we cannot do the same thing for KSPs. We cannot compare all ionic compounds to see which one dissolves more or which one has a greater solubility just by looking at the KSP. We can only do that comparison if we have two compounds that produce the same number of ions. That's the key thing here. Only if the compounds produce the same number of ions. And I will be showing you in a problem why that is the case, like why, if they don't have the same number of compounds, why the KSP is not going to be able to tell us which one is the most soluble. And here when I say that they produce the same number of ions, this is what I mean. So for example, calcium sulfide and magnesium sulfide, when they separate into ions, they separate into one cation, calcium or magnesium, and one anion, sulfide and sulfide, right? So they both have the same number of cations and the same number of anion moles. However, here this other example, calcium sulfide versus sodium sulfide. Notice that this one would separate into one calcium and one sulfide, while this one would separate into two sodiums and one sulfide. So for this scenario where you have different number of ions because of that too, we cannot compare the solubilities just by looking at the KSP. We would actually have to go in and set up the problem properly to be able to account for the different number of ions to find the solubility. But for this particular case, we can just go and look at the KSP value of these two. Whichever one has the greater KSP would have the greater solubility. All right. And as I mentioned, I will be doing some problems. Those are on slides 85 and 86 so that you can refer back to this later on and make sure that you understand what it says here. All right, in this slide, I just wanted to show you some of the values of KSP for a number of different compounds. And the reason why I put this here is not that you have to memorize it. In fact, you will have these tables available through either Sapling or in your exams that provide you those KSP values. But I wanted you to see how some of them can be actually very, very small. So something like 10 to the minus 33, right? That means that those compounds, those particular compounds, are going to have very, very low solubility relative to something that has a solubility in the order of 10 to the minus 3 or something like that. And of course, you guys remember a little bit of the solubility rules, I hope. Remember that compounds that had nitrate were considered soluble. And so that kind of shows you here, this is actually a fairly soluble compound or sparingly soluble compared to something that is at 10 to the minus 33 or 10 to the minus 26 or 27, which is a very small K relative to all of those Ks that we have worked with in the past, like Kas, Kws, those were all bigger than these are. All right, so let's start with the first problem. In this particular case, we're going to try to find KSP from solubility. So what we have is a saturated solution of magnesium fluoride, which is in contact with undissolved solid and is prepared at 27 degrees Celsius. All right, what they just told us here in this sentence is that we have magnesium fluoride, which is an insoluble compound. And because of that, it is a saturated solution. And I have both the dissolved ions, a little bit of them, but I also have a solid left over. So it's just telling us that we have an equilibrium between the solid compound and the ions. Then we are told that the concentration of the magnesium ions in the solution is 1.2 times 10 to the minus 3. So they have given us the concentration of one of the two ions. The question is, what is the value of the KSP for magnesium fluoride at this temperature? So the way that I would begin this problem would be to write the equation, the dissolution equation, or the equilibrium equation, if you would, between the magnesium fluoride as a solid. Oops, what did that do? So 2 as a solid. It's not letting me do. Oh my goodness. I'm trying to put a parenthesis, but it has decided that it does not like parentheses and that it is going to act super slow. Great. Okay, so continuing on. We have our magnesium fluoride as a solid, and that one is dissociating into magnesium ions, 2+, because it's in group number 2, And fluoride ions, fluoride has a charge of -1, and that one I need actually 2 of those ions. Both of these are actually aqueous. They are soluble ions. The ions will always be considered soluble. From there, I'm going to write my KSP expression. So KSP is going to be equal to the magnesium ions. Sorry, this is acting up on me. Magnesium ions to the power of 1, and then the fluoride ions to the power of 2. All right, now we have to think about what other information we have. We actually were told that the concentration of the magnesium ions was equal to 1.2 times 10 to the minus 3. And I want to come and write that here. So this guy right here is 1.2 times 10 to the minus 3 molar. And we don't have any more information, but we need to find KSP. And to find KSP, we need not just the concentration of the magnesium ion, but also the concentration of the fluoride ions. So this is where we need to think about this a little bit more. So as we know, basically to prepare this saturated solution, what we did is that we took water and we added magnesium fluoride to it. So the only source of magnesium ions and the only source of fluoride ions was the starting magnesium fluoride. And for every 1 magnesium ion that I make 2 fluoride ions. So if the concentration of the magnesium ions is 1.2 times 10 to the minus 3, then the concentration of the fluoride ions needs to be twice that. So 2.4 times 10 to the minus 3. And again, the reason for that is that that magnesium fluoride is the only source for the magnesium and the fluoride ions, and so their ratios are determined by those coefficients, a 1 to 2 ratio. Now that I have those two, I can actually come back in here and plug that information in. So for magnesium, I'm going to put my 1.2 times 10 to the minus 3. For the fluoride, I'm going to put 2.4 times 10 to the minus 3. And of course, don't forget to square that one. And once you plug the numbers in, you would get that your KSP is going to be equal to 6.9 times 10 to the minus 9. And we are done. Happy face. All right, so now that we have completed the problem in which we found the value of KSP from concentration of the ions, what we're going to do now is to learn how to calculate the molar solubility of a compound utilizing the KSP. In this particular example, which is from your book, we have calcium hydroxide, which dissociates into calcium ions and hydroxide ions. Notice that we're basically setting up an ice chart with the initial, the change, and the equilibrium. We're actually not going to be putting a number for the calcium hydroxide because in this particular case it is considered a solid, and so it is really not going to participate in the equilibrium and is present in excess, meaning that the concentration is so high that even though some of it is dissociating or dissolving, the concentration is really not going to change. So what we're going to do is that initially for the ions, we're going to put 0 and 0. For the change, we're going to have a little bit of a negative x for the solid compound, and that the products are going to be positive x, and for this one, oops, this is a positive 2x. I apologize for that typo. Positive 2x. And of course, we really don't care about the equilibrium for this guy because it will not appear in the equilibrium. But for our ions, we have 0 plus x, which is equal to x, and 0 plus 2x, which is equal to 2x. We can then take the equilibrium line to set up our KSP expression. That's solubility product constant is going to be equal to the calcium ions raised to the power of 1 times the concentration of the hydroxide ions raised to the power of 2, and that's what we have here. We then go and replace the equilibrium line into each of the concentrations. So the calcium becomes x, the hydroxide becomes 2x, and that 2x is squared because of the exponent that we had here, of course. And finally, we do the math here. So 2x squared is basically 4x squared. What I mean is this: once you get rid of of these two, it becomes 4x squared because the 2 gets squared and the x gets squared. And that is multiplied against the x to now become 4x cubed. Now, in this particular case, what we're looking for is the solubility. That molar solubility is actually going to be equal to x. It will be equal to x in any of the problems that we do. Again, the molar solubility is going to be equal to the x that we use on our ice chart. So what we're doing now here is that we have KSP is equal to 4x cubed. We then solve for the x by taking KSP divided by 4 and then taking the cube root on both sides to solve for x. So we get that x is going to be equal to the cubed root of KSP divided by 4. Now, how would you do this in your calculator? You would actually type KSP divided by 4. So whatever the KSP value is from a table, divided by 4. Oops, sorry, my computer is acting up again. Divided by 4. You would find what that number is, and then most likely your calculator is not going to have a cubed root. So what you might have is an ability to put it to the power of 1/3. 1/3 is the cube root. And if you are not able to do power of 1/3, you can do to the power of 0.33, which is the value of 1/3. All right. So this kind of process is exactly what we're going to do for any ionic compound. We're going to set up an ice chart where the reactant, it doesn't really matter. But for the products, we're going to have x if the coefficient is 1, 2x if the coefficient is 2, 3x if the coefficient is a 3. We then set up our KSP with the products only and we solve for x, where x is your molar solubility. We're going to be looking to find the solubility by utilizing the KSP. The KSP for copper A side is given as 6.3 times 10 to the negative 10. The question is, what is the solubility of copper A side in water? Solubility is asking for the concentration at which this compound dissolves. On the other hand, we were given the value of the KSP. To begin this problem, we're going to be writing the equation for the dissolution of that compound. So we begin with the copper A side, which dissociates into copper ions plus A side ions. The A side, we actually, or you guys might not know the charge for it, but we can figure out by looking at the formula here. So that 2 belongs to the charge of copper. So therefore, the 1 that is implicitly here would be the charge of the A side. The copper is positive, so the A side would need to be negative, so it would be a -1. We then have to balance the equation by looking at the fact that the formula says that there's 2 of those A sides, so we're going to put a 2 here to balance the equation. The next thing that we're going to do is that we're going to be writing a KSP expression, which is going to relate the concentrations to the KSP value that we were given. But to do that, we need the equivalence, the equilibrium amounts. And so we're going to set up an ice chart to be able to figure out our equilibrium. We're actually not going to put anything here for the reactant. This is a solid. That solid, remember, that is not going to end up in the KSP expression, so it doesn't really matter what we put. In the previous problem, what we said is that we have an excess of that solid because that one is present in a very high concentration, much more than what can actually dissolve, and so we can treat it as if it was constant, basically. The change is going to be a -x for that copper A side, but of course we don't really care. There's no equilibrium value for it. On the other hand, we're starting with 0 and 0 of our products, right here, and the change of -x is going to be carrying as a positive x on this side for the copper because its coefficient is a 1, but for the A side it's going to be positive 2x. Oops, I'm not sure why it's doing that. 2x for that A side because of the coefficient being a 2. For the equilibrium, we of course don't care for the copper A side because it's a solid. But for this guy, we're going to have 0 plus x, which is equal to x, 0 plus 2x, which is equal to 2x. So that right there is our ice chart. From there, what we're going to do is to use our equilibrium values to place them into the KSP expression. So give me a second, I'm going to make a little bit of room here. There we go. All right, so we're now going to write the expression for our KSP. Remember that the K is always products over reactants, but the reactant in this case is a solid, so we will be omitting it. So I'm just going to put the concentration of the copper ions, times the concentration of that A side ions to the power of 2. That 2 is from the coefficient for that A side. We are going to omit the reactant because it is a solid. We know the value of the KSP, and so now what we're going to do is that we're going to replace the equilibrium concentrations here by using what we have on our equilibrium line. So KSP is going to be equal to, for copper, it is an X. For the A side ion, it is a 2X. And of course, that 2X is going to be squared because of the exponent that we have here. When you square 2x squared, that becomes 2 squared, which is 4, and x squared. So 4x squared here times x, that becomes 4x cubed. So that's what I'm going to write here. Now I have KSP is equal to 4x cubed. Sorry. From there, we're going to solve for x. So first thing I'm going to solve for x cubed. The x cubed is going to be equal to my KSP divided by 4. I then take the cube root of both sides, and I end up with x is going to be equal to my KSP. Let's see if it lets me write. No, does not want to. Come on. Okay, let's try that again. Come on, please work with me. KSP divided by 4 to the power of 1/3, which is the cube root. And now we can plug in the values. The KSP is, if it lets you, you can put in the values. Maybe I will have to type it. Let's give that a try. It doesn't want to let me type either. Wonderful. Let's try it again. Okay, parenthesis, please. KSP is 6.3 times 10 to the negative 10 divided by 4, all of that to the power of 1/3. And you should get 5.4 times 10 to the minus 4 molar, because it is a molarity quantity, right? The quantities that we have here are in molar units, therefore the X is going to be in molar units as well, and that is a problem. So just to recap, to find the solubility from KSP, you're going to set up an ice chart where really what we're getting to is what is at the equilibrium. And in the equilibrium, you could actually directly go to the equilibrium without actually setting up the whole ice chart, because you know that you're starting with 0 for the products, and the changes are simply associated with the coefficient. So if the coefficient is 1, you would have 1x. If the coefficient is 2, you could have 2x, and you could simply go directly to that equilibrium. We then utilize this to plug it into the KSP expression. And if we're looking for the solubility will be equal to x. No matter what compound it is, the solubility will always be equal to x. All right, in this clicker question, what we're trying to find is which one is the most soluble out of all of these compounds. And we are provided the KSP values for them. Remember that a few slides ago, I told you that you could only compare the KSP values and determine which one is most soluble by comparing those if the number of ions that these compounds made was equal. So for example, when I dissociate lead chloride, it actually forms one lead cation, lead 2+, and it forms 2 chloride ions. So that means ions. So that means that we have a total of 3 ions. If you look at the calcium hydroxide, it would form 1 calcium ion and 2 hydroxide ions. So that's a total of 3 ions. The next compound, the iron hydroxide, it would form 1 iron ion and 2 hydroxide ions. So again, a total of 3 ions. And then the last one, this silver chromate, we're going to have 2 of the silver ions and one of the chromate ions, meaning that we also have a total of 3 ions. So because of the fact that we have the same number of ions from all of these 4 compounds, we are able to simply compare the KSPs of one another, and based on that determine which one is the most soluble. Now let's think about, do we want the highest KSP or do we want the lowest KSP? Remember that we said that since the KSP is telling you how much concentration of the ions you have that have dissolved, the higher the KSP, the higher the solubility. In this particular case, we are looking for the most soluble, which means that we are going to be looking for the one that has the highest KSP. And in this particular case, the one that has the highest KSP is the one that has the smallest negative exponent here, which is going to be the lead chloride. Again, make sure that you only do that rationale can only be applied if you have the same number of ions. If we have different number of ions, which is going to be the next problem, we're going to have to actually do some calculations. All right, so the next question is, which of the following is the least soluble in water? And we have a total of 5 compounds. All right, so this one is going to be a little bit harder, and hopefully you can see that immediately. The first 3 are all silver compounds that have 2 ions. So silver chloride has 1 silver, 1 chloride ion. This one has 1 silver, 1 bromide, and 1 silver, 1 iodide. So these 3 we could compare, and from those 3 we could eliminate the most soluble ones. The most soluble ones would have the higher KSP. So we could go ahead and eliminate some. We could eliminate this guy and this guy because the silver iodide has a smaller KSP, and therefore it is least soluble out of those 3, right? And again, we compare them because they have the same number of ions, but the other 2 compounds have different number of ions. While these had 2 ions, 1 cation, 1 anion, this one is going to have 2 of the silver ions and 1 of the chromates, which is a total of 3, and then this one would have 1 of the silver ions, I'm sorry, not 1, 3 of the silver ions, I apologize because of these 3, and 1 of the arsenate ions, which means that we have a total of 4 ions. So we therefore cannot just look at the KSP to figure out which one is the most soluble. We're actually going to have to go and find the solubility. We're actually going to have to go and find X. Because of technical difficulties, I had to actually do this by hand, and I will present the solution to you guys. Basically, what we're going to do is that we're going to take the first of the 3 compounds that we're trying to compare the solubility of, which is silver iodide in this case, and we're going to write the equation for its dissolution. I have now set up a simplified ice chart here in which basically I go directly to the equilibrium line. Remember that we start with 0 of each of the ions. We then do the changes, which in this case are going to be positive X and positive X because their coefficient are 1 and 1. And so we just end up with X and X. So as I'm saying, basically you can go directly to the equilibrium line where you just put as many X's as the coefficients that you have, right? We then set up our KSP expression for that silver iodide, which is going to be equal to the concentration of silver ions times the concentration of the iodide ions. And then we replace those concentrations with our x's. So for each of them is going to be x, which means that we have KSP is now equal to x squared. I need to solve for x, so what I do is that I take the square root of both sides and I end up with x is equal to the square root of KSP, which is equal to the square root of 1.5 times 10 to the minus 16. Remember that that number was provided to us in the problem. Once we take the square root, we find that the solubility is 1.2 times 10 to the negative 8 molar. We then do the same thing, and this is something that we're going to find at the end. But we then do the same thing with the silver chromate. In this case, our equilibrium line is going to have 2 x's for the silver because of the fact that it dissociates into 2 silver ions and 1 chromate ion, and therefore 1 x for that chromate. We then set up the KSP expression as silver ions squared times the concentration of the chromate ion to the power of 1 because its coefficient is 1. We then input the x's, so for silver it becomes 2x, but the square remains. For chromate it's just x, and that's what we put here. Then we square everything that is inside of the parentheses. So 2 squared is 4, x to the power of 2 is x squared, and then times x. And then we multiply everything out, so we get 4x cubed. We then need to solve for x, so the first thing that I do is divide both sides by 4 to get x cubed is equal to KSP divided by 4, and therefore x can be equal to the cubed root of KSP divided by 4. We then plug in the numbers and we get that x is equal to 1.3 times 10 to the negative 4 molar. From there, we go to the third compound, which is the silver arsenate. And we do the same thing. We dissociate it into the ions that it is made out of, which is the silver ion, which remember has a charge of +1, and then the arsenate ion, which has a charge of 3, but negative, of course. We then do our equilibrium line, which is going to be 3x for the silver ions and 1x for the arsenate ions. We set up our KSP expression as the silver to the power of 3 times the arsenate concentration. And then we replace it with our x's. So the silver ion is 3x, but still cubed, and the arsenate is simply x, which is what goes here. Now, 3 to the power of 3 is 27. X to the power of 3 is x cubed. And then we multiply this two parentheses out, which gives us 27x to the 4. And that's what we have here. We are still looking for x, which is the solubility. So the first thing that I do is that I divide both sides by 27 and end up with this equation. And then we need to get rid of the fourth here, right? So that means that we need to take the fourth root, if that's the way to say it, which means that I'm just going to take whatever I have on the right and put it to the power of 1/4. Again, I highly recommend that you guys look to see how to do this in your calculator. In some calculators, you can type it like this. In some calculators, you could actually put the root of whatever number you want, like it can be square root, cube root, fourth root, or whatever root you need. In some calculators, you might have to raise it to the power of 0.25, which is what 1/4 is. And so play with it, and if you have any trouble with that, please send me an email and we can set up a Zoom meeting to see if I can help you out, okay? All right, and so we end up with our final solubility for the silver arsenate as 4.5 times 10 to the minus 6 molar. The question initially was, which one is the least soluble? And so as you can see, by comparing the solubilities of these three compounds, the one with the smallest solubility is the silver iodide. So that's how we have solved the problem. Silver iodide is the answer. And just to recap again, if you have compounds that have the same number of ions, such as silver iodide, silver bromide, silver chloride, you can simply look at the KSP, and based on that, you can figure out which one is the least soluble because it would have the smallest KSP. But if you are comparing compounds that have different number of ions, like 2 here, 3 here, and 4 here, then you need to do the calculations to figure out what is the value of the actual solubility, which is the value of x.